Hi, welcome back to College Algebra, and this week we're going to talk about graphs of functions and system of linear equations. We'll cover 2.7, 3.1, 3.2 from our textbook, and please look over these slides to understand the measurable outcomes for this week. 2.7 graphs of functions. Let's talk about linear functions and constant functions. So linear function is a function that has the form mx plus b, where m and b are constants and m is not 0. And a constant function is a function of the form f of x is equal to b, where b is a constant. Both of these functions have, when you graph them, it looks like lines. The constant function is a line that is horizontal. Every input has the same constant output. General linear function looks like this, where we talked about this before, where there's a slope and a y-intercept. So here's a function that is called quadratic functions. F of x is x squared. The domain is all real numbers. Any input has an output, so the domain is all real numbers. And so here's some inputs and outputs. Again, if x is the input, then f of x is taking x and squaring the value. And so 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. And if I plot those points and connect the dots, then I have a shape that is a U shape or a parabola. Here's another common function, 1 over x. Notice that the domain does not include 0, because I can't not divide by 0. And so the domain is all real numbers, not including 0. And then usually with these functions we try to plot out some values and kind of get a rough picture of what they look like. So if I plug in some points, any input, the output is just a reciprocal. So notice that as x gets bigger on the positive x-axis, then 1 over x gets smaller and smaller. And then x gets more and more negative. F of x also get close to 0, but this time it will be on the negative side. And then notice that when x is really close to 0, 1 over x is really, really big. Similarly, if x is really close to 0 on the left side, 1 over x is really, really small. So this is the picture of 1 over x. And then this line, the x-axis, is also known as the horizontal asymptote, because the function is approaching that line in both the positive infinity direction and the negative direction. And then this vertical line is called vertical asymptote. The function is approaching it in the vertical direction as x approaches 0. So here's the summary of some basic functions that we should know. Especially we should know the domain and the graphs and the names. So f of x is x. This is the identity function. Every input, it has the same output. So this is just a line that is 45 degrees, cuts y and x at the 45 degrees angle. And then the f of x is x squared. It's a quadratic function. It's at the U shape or parabola shape. The domain of these functions is all real numbers, and the range for the first function is all real numbers, but the range for the quadratic function is only the non-negative numbers. And then the cubic function is x cubed. Looks like this. Domain is all real numbers. The range is also all real numbers. So again, please know these basic functions. Later in the class, we're going to need to know some of these functions to create new functions. So here's another one. This is the absolute value function. It has the V shape. On the right side is just the identity function. On the left side is the negative identity function. So it's that V shape. And so the range is from 0 to infinity, including 0. The square root function, the domain is, notice only non-negative numbers. You cannot take a root of a negative number. And so there's no output on this side. And this is the shape of the square root function. And finally, the reciprocal function, as we saw in the example previously, looks like this. Okay, let's look at general quadratic function. We saw the power function x squared. Quadratic function is a function that has the form ax squared plus bx plus c, where a, b, c are real numbers, and a cannot be 0. And we'll spend some more time on quadratic function in a future lecture, but right now all we need to know is that the graph of the function has the shape of a parabola. The coefficient a tells you the direction of the parabola. If a is positive, then it opens up. If a like this, if a is negative, it opens down. And this point is called the vertex. is the minimum when it opens up, and it's also the maximum when it opens down. But again, we'll spend more time on this quadratic function in a future video. So let's look at these functions, make sure we know the difference between linear, constant, quadratic function. So A, this is a constant function, output is always the same. B, this is a quadratic function. C, this is a linear function, has a slope and a y-intercept. This is also a linear function. Again, the slope here is 1/2, the y-intercept is 1, and then this is the one of the reciprocal function, and so it's none of the above. Okay, given a function, we need to understand a couple concepts, and one of them is the X-Intercept, and that's where the graph crosses the x-axis. So to find the X-Intercept, we set the function equal to 0, because when the function is equal to 0, then that means the y value is 0, and that's exactly where the function crosses the x-axis. And then to find the y-intercept, we plug in 0 for x. Okay, for example, let's find the x-intercept and y-intercept of this function. Again, to find the x-intercept, we set the function equals 0 and solve for x. So if I do that, I get x is 2, so the x-intercept is 2, 0. And to find the y-intercept, we plug in 0. So plug in 0, you get -4, so the y-intercept is 0, -4, because again 0 is x. So this function is linear, and if I have the y-intercept and an x-intercept, I can connect the dots and draw the line. So again, graphically, the y-intercept is where the function, the x-intercept is where the function crosses the x-axis. So in this case, is this point right here, x is 2, and the y-intercept is where the function crosses the y-axis. In this case, it's at y is 4, -4 rather. Okay, suppose I have a function that looks like this. Let's try to figure out what the x-intercept is and what the y-intercept is. So from look at this, here's the x-axis. So the x-intercept is all the points that crosses the x-axis. So it happens at -2, for example. That's an x-intercept, and +2, and also 3. So we have 3 x-intercepts: -2, 2, and +3. The y-intercept is where the function crosses the y-axis, and it is at y is equal to 6. And notice we can have multiple x-intercepts, but we can only have one y-intercept. That's because we're dealing with function, and for function, every input must have exactly one output, and so therefore we cannot have multiple y-intercepts. Okay, let's talk about system of linear equations. So we saw a linear equation of 2 variables previously, and now we might have a system of linear equations, something that looks like this. Notice again the constants here, the x and y are powers of 1, so this is a linear in x and y, and we have 2 equations and 2 unknown x and y. So we want to solve the system. So a solution to this system of linear equation is an order pair x, y that satisfy both of the equations. So for example, here's a system of equation. Let's try to see if these are solutions. If I plug in -2, -4 into the top line, I get that -6 is equal to -6, so that checks out. If I plug into the bottom line, again -2 is x, y is -4, I get that that we have an equality, so that is both of these are true, so therefore -2, -4 is a solution to the system of equation. But if I plug in 0, -6, I do get that the first equation is satisfied, but when I plug in the second equation, it is not satisfied. +6 is not equal to -2, therefore this is not a solution, because it needs to be a solution to both equations. Notice that when I look at these two lines, there's one common intersection point, and this is exactly at the point -2, -4, which is the solution point we saw earlier, and it's the only solution to the system. So the purpose of this part of the lecture is to solve a system like this. So how do we get this solution in the first place? Okay, so when we draw two lines, so if we talk about a system of two equations, linear equation, then there's only a few cases. If we have two linear equations, then there's really 3 possible cases. The two lines intersect at exactly one point. That's the case we saw just earlier. the two lines are parallel and they do not intersect, and so in this case there's no solutions. Or if the two lines are exactly the same, in that case it intersect at infinitely many points, namely all the points on that line. And so if you have a system of linear equations that has one or more solutions, the system has to be consistent. So consistent means that there's at least one solution, and if a system has no solution, then it's inconsistent. If two equations represent the same line, then all points along the line are solution to the system of equations. So if you have a case where you have two lines that coincide, or the case where there's infinite number of solutions, then the equation is said to be dependent. The two equations are equivalent, and they essentially are the same. And if two linear equations represent different lines, then the equations are independent. So let's kind of see. So again, you have one unique solution. In this case, then the system is consistent because there is a solution, and this is the equations are independent because there's only exactly one solution. In the case where there's no solution, the system is inconsistent because there's no solution, and again the equations are also independent in this case. And finally, when the system is consistent, because if you have two lines that are coinciding, then solutions, there's infinite number of solutions, so certainly that system is consistent. But because these two lines are the same, they are dependent. Independent means for these two cases they're not the same lines. Okay, let's look at this system and try to find the solution. So one way to do this is to kind of graph each equation. So the first line has slope 1/2 and y-intercept -2. And the second equation, we have to kind of let's put this in slope-intercept form. So if I put this in slope-intercept form, I solve for y, move the 4x over, divide by 2. Notice when I divide by 2, I have to divide by both of these. So the slope is -2, the y-intercept is 3. So notice the slopes are different. So that means that these lines will meet at exactly one point. And so if I were to graph it, then I get the intersection point here. Notice that for this method of finding a solution to work, we have to draw the graph exactly, and we might have to rely on graph paper to do this. So this method of finding a solution is not recommended because it's not always possible to find the exact solution. If the solutions are not nice numbers that has decimal point, then it might not be possible to graph it perfectly and find the solution exactly. And so we'll talk about later about how to find a solution in general, but again, graphing is very limited. So again, we can always check the point intersection, make sure that even if we draw it properly, we still want to make sure we check this because it's possible that we might make a mistake when we draw the picture. Okay, here's another one. So again, let's just put this in slope-intercept form. So solving for y gives me this on this side and also on this side. Again, please check over this on the slide carefully, the math. But we've done this before, so I'm going to skip through it. But notice that the slope is the same for both of these, but the y-intercepts are different. So that means that these equations are parallel and there's no solution. So the solution is the empty set. How about this one? Again, we always want to put in slope-intercept form. If we were to graph it, slope-intercept form makes it easier for us to graph the equation. Notice now, if I solve for y or put it in slope-intercept form, this one has slope -1/4, so is this. But notice that the y-intercept also is the same, so the two equations are exactly the same. So they coincide, and that means there's infinite number of solutions. Namely, all the points on the line, on the two lines, which is the same line, these are all solutions to the system. So in the case where the system, in this case, let's talk about how to kind of how do you describe this solution? Because again, in the case where there's one solution, it's easy. You pick the point is the solution. In the case where there's no solution, you say no solution. But in the case where there's infinite number of solution, how do we describe that solution set? So let's talk about that. So because these two equations are the same, they coincide, we can pick one of them because they're dependent, they're the same. We pick one of them, and one way to write the solution to say the set of all x comma y is such that this vertical line is such that the set of all x comma y is such that y is equal to -1/4x plus 2. Notice this is one of the two equations. Again, because these equations are the same, pick one of them and we put it in here as a conditional for all the points. All the points that lives on this line is a solution to this, and the other one therefore is a solution to the system. Another way of doing this is to say instead of our x, y such that x plus 4y is 8. In other words, we pick the other line, the other equation. So either of these equations these set notation will work as solutions. Let's talk about another way to describe the solution, and this is to use the x comma y notation where y is written as a function of x. And the reason why this is kind of a solution set, as we find out, will be something that you need to do, because on web work you need to kind of write the answer in this new notation. So the notation we discuss here will not be accepted on web work. So how do I do this another way? Well, we're going to write it in x comma y where y is a function of x. So if I take one of the equation, any one of them, and solve for y, then we get that 8 minus, so for example, if I solve for y here, I get 8 minus x divided by 4. So one way to write this solution set is the set of our points such that for x comma 8 minus x over 4. In other words, for any x, as long as the y value is given by this function, this means that all the points that are on this line or the other line, because they're the same. So this is basically another way of describing the points on this line. Again, the set of all x such that the y value satisfies the line equation. Another way of doing this is to say to use the other form of the line, and so the set of all x such that the y is a function of x, where this function is given by the second equation. So again, this kind of format is what you'll be expected to do on web work for this week. So please look at this example carefully. Okay, 3.2 solving. The last way of solving system of equation, we rely on drawing perfect graphs, and so that method might not always be reliable. We might not be able to find solutions that has a lot of decimal places exactly. And so here's another way to solve system of equations, is to use the substitution method. And in fact, this method can be used to generalize to a lot more system of equation other than a linear system. And so the method is basically to isolate one of the variables from one equation and then use substitution to substitute into the other equation and then solve the other equation. And once we solve the other equation, we can go back and substitute it to find the other value. So maybe it's best to kind of see an example of this. So again, isolate one variable. So for example, I want to take the top equation, isolate y, solve for y, or in this case actually solve for x. So x is 16 minus y, and take this and plug it into the x value of the other equation. Notice this first equation, this expression is plugged into the second equation right here, the x value. So plug into into here. So 16 minus y is 4. So this is the second equation. Now I solve for y, because now this equation has only one variable, which is the y variable. So combine the like terms, minus 2y, bring the 16 over, divide by -2, y is 6. Once you solve for y, you need to go back and solve for x. So I can take this y and go back and substitute into this equation, in fact any equation really, and to get the value of x. So for example, if I plug y, which is 6, into this equation, I get x is 10. And so we can check that this is indeed a solution. So let's try doing an example with the substitution method. So again, we will need to isolate one variable, and sometimes it's easier we gotta pick one of the equations might be easier to work with. So if I try to solve for x or y here, it's hard because I have to divide by 2 or divide by 3. That might cause us to have some fraction. But notice this second equation, y has a coefficient of 1, so it's easier to isolate y. So let's pick the second equation and solve for y. So that means that so y is equal to -6x plus 6. So again, solve for y here, and take this and plug it into the other equation, which is the first equation. Plug it into where you see where y is, and so 3x minus 2 times the y value expression equal to -7. So we want to solve for x now because everything is in terms of x. So we have to distribute the -2. So 3x, -2 times -6x is plus 12x. -2 times 6 is -12. Combine like terms. So when you solve for x, you get 1 over 3. Now that you have that, you can go back and substitute into x, into any of the equation, and to get the y value. So that's a solution set. Okay, how about this one? Notice in this case, x is already solved for, x is already isolated, so we can now use the substitution method by plugging this expression into the x variable. It's already been isolated, so I take this, I plug it into the other equation that has x into x. Then when I isolate, again, distribute this, make sure you're careful. This is a common mistake to not distribute. So -2 or 4y, and then plus 8, combine like terms. And notice that when we do that, we get 8 is equal to 6. This is a contradiction. So that says that the original system has no solution, and it is inconsistent. So that means that these two lines are parallel. They don't intersect. Therefore, there's no solution. Okay, let's do another one. Again, solving for y. Again, this one's harder to solve for x and y. So this one has whenever you have a variable that has coefficient of 1, then that's the one you want to work with. Solve for y, plug it back in. And when we combine like terms, we get that. Notice now the numbers -6 is equal to -6. So that means that this is an identity, and that means that the two equations are equivalent. That means that they're the same equation, and therefore this system is dependent and it has infinite number of solution. And again, we talked about before, we can write it in two ways. One way is to say the set of our x, y such that this equation is one of the equation, or we can pick the other equation. So either way will work. But again, this solution set would not work on WebWork. So make sure you look at the previous slide to see how WebWork accept the solution. Okay, let's end with an application of system of equation. So here's an application. Suppose you're at the amusement park and you bought 5 hot dogs and 1 drink, and that cost $22. And later you come back and you bought 2 hot dogs and 3 drinks, and that cost $14. Can you use those two pieces of information to figure out the cost of a hot dog and the cost of a drink? So this is set up for a system of linear equation. We're going to let h be the cost of 1 hot dog and d be the cost of 1 drink. And so let's convert these into two linear equation. So the first equation is that 5 hot dog plus 1 drink costs $22. So that means that we can, so again, the cost of 5 hot dogs plus the cost of 1 drink is $22. So again, h is the cost of 1 hot dog. So you have 5, that means that 5 times h is the cost of 5 hot dogs. 1 drink means plus d, because d is the cost of 1 drink. So 5h plus d is 22. And the cost of 2 hot dogs plus the cost of 3 drinks, so 2h plus 3d is 14. So we have a system of 2 equations, 2 unknowns, h and d. So we can solve by a substitution method or by a graphing method, but let's use the substitution method. Later we'll talk about another method called the addition method in the next video. So let's use the substitution method. So if I solve for d here, so that because d is easily isolated, and then plug it back into the other equation in d, and then when you multiply it out and then combine like terms, and you get that h is 4, and going back, plug 4 into the other equation gives you that d is 2. And so that means that because h is 4, the cost of a hot dog is $4, and d is 2 means the cost of a drink is $2. Okay, thanks for watching.